When I look back at the last few decades of computing, I'm struck by how much of this story is equal parts accident, engineering, and persistence. A misconfigured banner at budget that somehow prints money. A trial reminder that fires a little too often and teaches a lifetime lesson in user trust. A pile of cheap disks stitched together with clever redundancy that quietly outperforms a single expensive brick. Those moments feel small when you're in them, but they add up to the culture of how we build things. And as we keep climbing layers of abstraction, up from machine code to Python to natural language prompts, there is a danger of forgetting the gritty scientific roots, numerical stability, cache locality, reproducible parallel reductions, and the blunt limits of physics. I want to linger there for a bit in the engine room because that's where the most interesting progress is happening. In scientific computing, complex models, and the scaffolding that makes modern AI and simulation possible. Take the early 2000s story of banner ads that weren't kept and racked up $10,000 over a weekend, only to return nearly four times the spend in sales. That anecdote isn't just about luck, it's a parable about feedback loops. In scientific computing, we live inside feedback loops of a different kind. Run the code, measure the performance, examine the numerical error, tune the preconditioner, try again. It's A slash B testing for physics. If the solver diverges, you're explaining it to your spouse on Monday morning. If it converges 30% faster, you scale it across the cluster. The instinct is the same. Instrument, iterate, and let reality, measured latency, FLOPS, wall time, residual norms, tell you what's true. That instinct matters because modern scientific workloads are unforgiving. Simulating the Navier-Stokes equations in a turbulent regime, running a global climate model with coupled ocean atmosphere land components, reconstructing a brain connectome from petabytes of microscopy, performing seismic inversion to see a kilometer under the earth, solving Maxwell's equations for photonics, doing topology optimization for lighter aircraft parts. None of that's best effort. It's get the math and the machine right or the answer is wrong. People often imagine AI as the peak of complexity, but the world of partial differential equations and Krylov solvers is every bit as intricate, and it's had decades more time to refine its craft. Consider linear algebra, the lingua franca of both simulation and machine learning. At the bottom sits BLAS and LAPACK, highly tuned building blocks for dense linear algebra. On top of that, for sparse problems typical of PDEs, you get libraries like PETSK and TRILINOS with carefully engineered data structures and a menu of Krylov methods. Conjugate gradient for symmetric positive definite systems. GMRS and Bayes G-stab when symmetry goes out the window. Flexible GMRS when your preconditioner morphs mid-iteration. Preconditioners are the quiet heroes. Incomplete LU factorizations, algebraic multigrid AMG, geometric multigrid with V and W cycles, domain decomposition methods like additive Schwartz. People love to talk about the big O of an algorithm. In practice, the preconditioner decides whether your job is a 3-minute solve or a 3-day crisis. We can't talk about performance without talking about the roofline model, which frames the battlefield simply: arithmetic intensity on the x axis, attainable performance on the y axis, and two ceilings, one set by memory bandwidth, the other by peak compute. Most scientific kernels, from sparse SPMB to stencil updates, are brutally memory bound. That's why data layout, AOS versus SOA, tiling, blocking, alignment, prefetching matters as much as algorithmic cleverness. It's also why reproducibility is hard. When you parallelize, floating point non-associativity means summations in different orders produce slightly different answers. Kahan summation can help, so can deterministic reductions. But bitwise identical across thousands of cores is a negotiation between mathematics and the scheduler. Parallelism itself splits into two big worlds. Threaded parallelism on a node, OpenMP, TBB, C++, ST execution, and distributed parallelism across nodes, MPI. In the trenches, hybrid MPI plus OpenMP or MPI plus CUDA is the default. Coarse-grained domain decomposition across nodes with MPI, fine-grained loop-level parallelism within a socket or GPU. Amdahl's law reminds you that a tiny serial tail can kill scaling. Gustafson's law rescues you when you increase the problem size with core count. Sparse halo exchanges collide with network topology. Collectives like AllReduce become the heartbeat of both conjugate gradient solvers and data parallel training. If you've ever watched a Krylov residual stall because an all-reduced latency jittered on a congested factory, you've met the ghost in the machine. Fast Fourier transforms are another shared workhorse. In CFD, spectral methods use FFTs for Poisson solves and pressure projections. In imaging, FFT-based deconvolution is bread and butter. On GPUs, libraries squeeze performance by batched plans and fused transpositions that minimize global memory traffic. But even FFTs bow to physics, PCIe bandwidth, NV-link topologies, and UMA domains, all the boring details, decide whether your pipeline purrs or coughs. The same is true of multigrid. The perfect ON algorithm on paper collapses if your coarsening strategy clashes with your mesh partitioning and your coarse grid operator becomes a global bottleneck. Now, about complex models. In the AI world, complex often means billions of parameters in a transformer diffusion model or mixture of experts. In scientific computing, complex means coupled multiphysics, a climate model that ties radiative transfer to fluid dynamics, biogeochemistry to sea ice, and all of that to land surface processes, or a reactor simulation that couples neutron transport to heat transfer to material microstructure, or a PDE constrained optimization problem that backpropagates through a time dependent PDE solve, which is essentially training but with adjoints and optimality conditions instead of stochastic gradients. This is where modern automatic differentiation frameworks like JAX and PyTorch are sneaking into the scientific stack, enabling differentiable simulation. You write your PDE solver, mark it differentiable, and let reverse mode autodiff give you gradients with respect to parameters, boundary conditions, or even geometry. Physics informed neural networks, PINs, live here too, embedding PDE residuals into the loss so the network learns solutions under physical constraints. They are not the hammer for every nail, but they are powerful in inverse problems where data are sparse and priors are strong. If we zoom into Bayesian territory, complex means hierarchical models, Gaussian processes with structured kernels, and Markov chained Monte Carlo MCMC methods that actually mix. Hamiltonian Monte Carlo, HMC, and its adaptive cousin NUTS combine physics, inspired proposals with gradient information to explore high dimensional posteriors efficiently. Variational inference takes a different trade off. Approximate the posterior with a parameterized family and optimize a bound. In practice, A lot of real labs run hybrids. Amortized inference with neural surrogates for expensive likelihoods, then targeted HMC for final uncertainty quantification. Scientific credibility lives in those intervals and posterior predictive checks. Point estimates are easy, error bars are where the science happens. Complex models also show up in modal analysis, literally. In structural engineering and vibroacoustics, you'd solve generalized eigenvalue problems to find natural frequencies and mode shapes. The solvers, Langsos, Arnoldi, Jacobi Davidson, are fussy beasts. Preconditioning again makes or breaks you, and so does careful scaling of mass and stiffness matrices. In photonics, eigenmodes of Maxwell operators tell you how light will live inside a cavity. In quantum chemistry, coupled cluster methods chase excited states in spaces that explode combinatorially. These problems don't yield to vibe coding. They yield to decades of craft embodied in libraries, data structures, and the experience to pick the right numerical hammer. Tooling matters. On CPUs, vectorization SSE slash AVX slash NEON slash SVE is table stakes, and compilers need help. Restrict qualifiers, alignment hints, loop pragmas, and data layouts that make strides predictable. On GPUs, you decide between CUDA, HIP, Cycle, COCOS, Raja, each a bet about portability and performance. You think about occupancy, register pressure, shared memory tiling, warp level primitives, tensor cores for mixed precision, and whether your kernel is bandwidth or compute bound. For ML mixed precision, FP16 slash BF16 with FP32 accumulators is now default. For simulation, it's more delicate. Many PDE codes are experimenting with multi-level precision, double on coarse levels for robustness, single on fine levels for bandwidth, while monitoring residual growth. The science is in the guardrails. When do you reorthogonalize in GMRES? How often do you rescale a diffusion term? When do you checkpoint to avoid catastrophic state drift? Storage and data movement are the other half of performance. RAID was the entry level revelation. Cheap disks in arrays with redundancy, but exascale workflows rely on object stores and erasure coding, think Reed Solomon, across racks, plus tiered storage policies. Burst buffers of NVMe to ingest checkpoints at tens of gigabytes per second, spilling to parallel file systems for midterm and offloading to tape or cold object storage for the long tail. I/O dominates many production runs. A fast solver that checkpoints every minute with blocking writes can be slower to solution than a slightly lazier solver that checkpoints smartly and overlaps I/O with computation. Provenance systems matter too. When a mesh parameter file, compiler flags, and environment module versions aren't tracked, you can't reproduce yesterday's miracle speedup any more than you can recover a vanished weekend ad campaign. Benchmarks keep us honest. MLPERF has done wonders for cutting through hype in training and inference. In HPC, LINPACK drove the TOP 500 era, but HPCG arrived to penalize memory bound codes that better reflect real workloads. Both matter because numbers are stories that can be checked. The best engineering cultures agree on fair tests, publish them, and then let the chips fall where they may. That's as true for a Krylov solver as it is for a browser adoption experiment. If you reset the default to Edge via a recommend measured as nudge and watch weekly active users bump, congratulations, you've maximized a metric while nicking trust. In scientific computing, we've learned the hard way that gaming the metric eventually bites the science. If your solver converges faster by loosening tolerances, the wake in your CFD simulation detaches 2 meters too early and a wind farm loses a year of power curve credibility. All of this sits on top of floating point reality. IEE 754 is a marvel of compromise, and it's also the source of many late nights. Every time you sum a billion values, you choose an error path. Every time you multiply very small by very large, you flirt with underflow and overflow. Kahan summation, pairwise reductions, compensated algorithms. These are not niceties. They're obligations when you promise scientific answers. Reproducibility becomes a policy decision. Do we enforce deterministic reductions at some performance cost? Do we lock compiler versions? Do we ban unsafe met flags even if they promise 1.15 times? Serious teams answer yes to those questions by default and document the exceptions. And then there's the human side, the part that seems unrelated until you realize it governs everything. People on teams interpret prompts, warnings, dashboards, and emails with wildly different priors. What feels like a gentle reminder to you lands as a manipulative shove to someone else. In software, we call this UX. In HPC centers, it's often user operations. The same empathy that stops you from dark pattern defaults should guide your error messages and your job scheduler's back off behavior. It's the difference between an ally and an adversary. In a lab, the equivalent is how you write your README, how you name your config flags, how you document a convergence criterion. The numerical method can be perfect. If the person running it feels gaslit by the interface, the system has failed. Let's bring AI back into the room with a scientific lens. Transformers, diffusion models, mixtures of experts. These are not just shiny toys. They're infrastructure for surrogates, emulators, and hybrid models. You train a convection surrogate to emulate a stiff subgrid process in a climate model, and suddenly your time step doubles. You use a diffusion model conditioned on physics based constraints to propose initial fields for an inverse problem, and your optimizer stops wandering the desert. You build a Gaussian process with a kernel that respects symmetries and non stationarity, and your uncertainty estimates stop lying to you. The maturity path is the same as it was for FFTs and BLAS, from curiosity to library to backbone. The people who will win here aren't the ones with the biggest model. They're the ones who make it easy for the field solver team to drop the model in, verify it against baselines, and turn it off when the edge case arrives. We can even talk about reinforcement learning without leaving the scientific world. RL for control of plasma in a tokamak, for adaptive mesh refinement that targets error hotspots, for online tuning of preconditioner parameters in response to drift. These are all happening, but again, it's engineering. Reward shaping, safety constraints, simulators faithful enough not to teach the agent bad habits, and a deployment architecture that keeps the RL policy on a leash. Vibe coding a controller is a good way to blow up a reactor. We write specs, prove invariance where possible, and watch the logs like a hawk. Programming languages are the palette. C and C++ remain the bedrock in production HPC because you can reason about layout and squeeze cycles. Fortran is alive and well where arrays and numerics are king. Rust is elbowing in with the promise of memory safety without sacrificing performance. And it's particularly interesting for writing boundary code that glues unsafe kernels to the rest of the system. Julia is the scientist's dream. Multiple dispatch, JIT specialization, and an ecosystem, differential equations.jl, GMP, Trixie.jl, that makes exploratory numerics sing. Python orchestrates the world. NumPy, SciPy, JAX, PyTorch, because its ecosystem and readability make it the lingua franca of collaboration. In the GitHub Prime spirit, fair comparisons teach humility. Compilers, not slogans, decide who wins on Tuesday night. And even when a language is slower, developer speed plus library leverage often crushes raw flops in wall clock science to paper. The future of programming will look more like architecture than carpentry. We will still carve custom joints, hand tuned kernels, exotic preconditioners, but more of our day will be spent describing constraints, objectives, and interfaces to systems that synthesize the scaffolding. Autotuners will search tile sizes. Compilers will fuse loops across languages. AD systems will propagate gradients through PDE timesteps. Schedulers will move data to where the compute is rather than the other way around. We will ask for a diffusion advection reaction solver on a curvilinear mesh with Dirichlet on gamma 1 and Robin on gamma 2. A joint enabled mixed precision on fine levels and checkpoints overlapped with compute. And the stack will assemble something sane. Our job will be to specify what sane means, to draw the safety boundaries, and to know when to drop a level and fix the leak ourselves. If this sounds abstract, it isn't. A weather center that shortens its 7-day forecast cycle by 40 minutes while keeping skill scores constant is not just saving money, it's enabling more runs, more ensembles, better evacuation notices. A hospital that reduces a diffusion MRI pipeline from 12 hours to 90 minutes by rewriting a couple of kernels and moving to a batched FFT on GPUs is not just shaving time. It's turning an overnight batch into a same day decision. A materials lab that replaces a month long DFT sweep with a surrogate model and validates it against a small ground truth set is not just clever, it's discovering alloys before a competitor. The connective tissue across these wins is the same. Careful numerics, honest benchmarks, principled engineering, and empathy for the humans in the loop. I started by talking about those accidental lessons. Banner ads with no cap, default checked disks that triggered a legal headache, trial pop ups that were technically polite but emotionally annoying. The parallel in scientific computing is real. You can underspecify a tolerance and declare victory. You can choose a faster but sloppier reduction. You can default a user into a setting that makes your solver look great in a demo and awful in production. Those shortcuts always cash out later as trust debt. The longer I do this, the more I think the most valuable commodity we produce, more than code, more than papers, is trust. Trust that our numbers mean what we say they mean. Trust that our software tells users the truth, especially when it's inconvenient. Trust that our fancy models degrade gracefully outside their training diet and don't bluff when they don't know. So here's my credo for whatever it's worth. Build cool stuff, yes, but build it on bedrock. Learn the numerics well enough to know when they can lie. Profile until you can draw the roofline from memory. Make defaults boring and honest. Put guardrails around speed. Treat users like collaborators, not conversion metrics. When you add a feature, include the plot that shows where it fails. When you publish a benchmark, ship the script. When you get a miracle speed up, Suspect the miracle before you celebrate it. And when you finally see it all come together, the solver converges, the posterior narrows, the mesh adapts where it should, the throughput doubles without cheating. Let yourself enjoy it. That feeling is why most of us started. The quiet satisfaction of watching something complex do exactly what it should. Maybe the meaning of all this is simpler than we make it. Make things that work. Make them useful to other people. Make them understandable enough that someone else can carry them forward. Measure fairly. Admit uncertainty. And whenever possible, leave a trail of breadcrumbs. Test cases, notes, small examples, so the next person doesn't have to start from zero. If we do that, the layers of abstraction won't feel like a hollow tower. They'll feel like a well built bridge, strong underneath, smooth on top, and ready for whatever traffic the future sends across it.